Yep. So, hi everyone. As you have already probably read from the title of the lecture, is that we are going to talk about addresses and transactions in Bitcoins. And in addition to that, we will also look at a few interesting graphs which provide some interesting insights on the numbers and statistics of Bitcoin operation. First of all, let's get a very brief reminder of how Bitcoin address is created. So first of all, a key pair needs to be generated, and as I believe you all know, key pair is generated according to the elliptic curve digital signature algorithm. We start with a private key. A private key is a certain random, ideally truly random natural number from 0 and to the order of a base point -1. This number is used as a scalar multiplier for the base point. By adding this base point of the curve to itself, so we perform addition, so point plus point plus point plus point n times, and the number n is our private key. So if our private key, let's say 4, just a very stupid example, it will never be 4, but let's say our private key is 4, natural number, then the public key would be this base point multiplied, added, not multiplied, added to itself 4 times. So point plus point plus point plus point. This will be the public key. And private and public key constitute a key pair. Once we have the key pair, we can hash it, and we have to hash it. The public key is hashed using proper algorithms which are specified in the protocol, and we will talk about that later. Once the key is hashed, we add the version byte, the checksum, cryptographic checksum, and encode the resulting byte string to receive an address that can be passed around and used as the identifier of the recipient. By knowing these two things, the version byte and the hash value, transaction creator can know what conditions must be specified in transaction output in order for the owner of the key to obtain these coins. Now let's look at this process in a more graphical way. So we start by default. Public key can be either 64 bytes or 33 bytes. It is for a compressed public keys. Then the resulting bytes are hashed with SHA-256 algorithm, which gives us a hash value with a size 256 bit. The resulting hash value, so we public key here, we hash it, get some hash value after that, and the resulting hash value is hashed again, but this time with RIPE-MD 160, resulting in 160-bit or 20-byte hash of a public key. These functions are both safe enough to prevent cracking them, and by cracking we mean finding the original value by knowing only the hash, so by reversing the hash function. So both of them are strong enough so that it is almost impossible to reverse the hash values and get the original value in some adequate amount of time. This means that the public key is protected because it is hidden behind the hash value. So even if a threat actor can crack a digital signature algorithm, so basically this threat actor can substitute the signature of this person who has this public key and this address, it will not be possible to execute the attack and steal the coins because it is impossible. The public key is unknown, so you cannot forge the everything, and you cannot derive eventually, if you have all this computing power and everything, you cannot derive the private key from the public key, and you cannot do the forging process. So it is impossible. And this means that in order to conduct a successful attack, the attacker has to crack both of the hashing algorithms. So he needs to reverse first RIPE-MD 160 and then reverse SHA-256, and then crack the digital signature algorithm as well to forge the digital signature and substitute it with his own digital signature. And that's why, in order to secure your coins more and secure your operations with Bitcoins, it is generally recommended to use one Bitcoin address, only each Bitcoin address only once, because the next time, once you unlock the coins, everyone will know your public key. And most Bitcoin wallets, they follow this convention and create, by default, they create Bitcoin addresses for each new payment. So you have, you use your Bitcoin address only once to receive a payment or receive a change from the transaction, and then you create a new Bitcoin address so that you hide your actual public key behind these two hash values. So once we have the hash of a public key, we add a version byte to it, and version byte is simply a special value which determines the, well, so first of all, the version byte itself will depend on the type of coin spending conditions that will be specified in script pub key, so that the sender can know how to construct the transaction. So this is simply a flag, so to say, so that we know how to properly construct the transaction. Conditions that are not standardized and cannot be represented by this version byte, of course, they can be used, and well, they will have no dedicated version byte, but they can be used. However, you will need to manually set conditions in script pub key, and of course it's less convenient, and it may require additional validation, as we have mentioned on one of the previous lectures, that although nodes will validate transactions that are valid but unconventional, so to say, they might expect bigger fee, and they might not do it so eagerly as they do as they validate transactions with the standardized proper version byte. So once we have done all of the steps, we add 4 bytes of checksum, and checksum is calculated by double hashing the resulting hash value. So we take everything, hash twice, then we cut only 4 bytes from the resulting hash, and this will be the checksum. Then we smoosh it all together, so we get a version byte first, then 20 bytes hash of public key, this one, then 4 bytes of the checksum, and it gives us 25 bytes in total. The resulting byte string is encoded with base 58 algorithm, for example, or it can be different. We will get to that later. And the final Bitcoin address usually has up to 35 symbols in it. But of course, there can be some deviations because of base 58 algorithm, because of the way it works. But this encoding algorithm is not the only one which exists in Bitcoin. When segregated witness update was introduced, it brought a new address format, which is called BAC32. And BAC was chosen because it sounds kind of similar to base. So like base, the base of this format consists of 32 letters of the alphabet. So it's called BAC32. Additional advantage of this encoding approach, of this encoding algorithm, is that 32 is the power of 2. To be precise, it's 2 to the power of 5. And computers, it just it just happened so, based on the process how computing technology was developing, that computers like to work with numbers that are the power of 2, like 2, 4, 32, and so on. So that's why it will be more effective when we calculate this encoding on a conventional computer. Of course, we are not talking about some computers that are working with different enumerational systems, or some very specific computers which may or may not exist, but for conventional computers, it is what it is. So what else we have to know about this format? BAC32 addresses are considered to be native segregated witness addresses because they are tightly associated with this update. For most of its history, Bitcoin has been using base 58 encoding with the addition of the control sum, which, as we know already, is the truncated result of the double hashing. And both of these, wait, before we go to this one, it's important to note that once BAC32 was introduced, the original base 58 encoding remained. It did not disappear. It did not go anywhere. It remained, and it is still fully supported by Bitcoin software, although using BAC32 is recommended but not mandatory. Yep, and it is recommended because it allows to pay lower fees, and well, because the addresses are less and they take less space and so on. Old addresses were part of the original software, and their scope has been extended in BIP 13, Bitcoin Improvement Proposal number 13, for pay-to-script hash, which allowed to use the hash of spending conditions instead of encoded conditions themselves. This is a pretty interesting concept, which allowed to have more effective operation of the system. And this hash value, in turn, can be encoded as a regular Bitcoin address, which is, well, pretty neat, if you ask me. However, both the character set and the checksum algorithm have their own limitations. So let's look at what limitations do we have for base 58 encoding. An address in base 58 takes up more memory when being converted to QR codes, well, because it's longer, so the QR code will be larger, and it will literally take more space on the screen, on the paper, or whatever else you are planning to put this QR code. Yep, and the reason for that is because it cannot use the alpha mode digital representation. Also, base 58 is very inconvenient for proper, adequate, reliable writing on paper, typing on a mobile keyboard, or reading aloud when you are calling on the phone, or you are talking to the person and you cannot show them the address, and you name every letter in this encoding. Because it includes numbers, small and capital letters, this is really inconvenient because you have to say every time A capital, B small, D capital, and so on. And this is very inconvenient. And when you're reading it on the paper, or you are seeing it in a on the screen of the computer, some fonts do not have proper visual separation between, for example, capital O and 0, so it will be easy to mix them up and write the wrong character, which will completely well, which will be pretty painful to deal with later. Also, double hashing of the checksum is slower because, and especially it is a problem on the devices with lower computing power. And the encoding algorithm itself is complex and relatively slow. Now let's look at a few examples of back32 addresses. And well, as you see, comparing it to the base 58, it does not carry most of the disadvantages that that exist in base 58. So this algorithm solves a lot of problems that base 58 has. Interesting fact to consider is that the resulting string is around 50% longer than it would have been with base 58 because we have the smaller base, so only 32 characters, and we need to use more characters. But it means that the encoded string itself is more consistent and easier to read. So here we, for example, have we have some addresses. Each of them has a prefix. So BC means mainnet. This is the prefix for the mainnet, and TB is the prefix for the testnet. And well, here we see the values, and even in this font, for example, which has the this thing to denote that we have 0 and not O, it's still easier to read because all of the letters are small. We have no capital letters, and we have only letters, small letters and numbers, which is easier. And here we have pay to witness script hash. You see that it is a bit longer because overall same rules apply to pay to witness script hash, but the hash value size is 256 bits instead of 160 bits. And that's why the final address will be longer, because we need to encode larger hash value. And just a small remark, which should be pretty obvious by now, is that these encoding algorithms, and well, practically any encoding algorithm, produces a variable output string. So unlike hash algorithms, which always produce a string of the same size, encoding algorithms produce different sizes of the string, because if we need to encode only 1 or 2 characters, we don't need to have a very long string. It's simply there's nothing to put in the string, and that's why well, there's not really any sense to have it larger than it needs to be. And on the other hand, when we want to, let's say we want to encode some text even with base 64, for example, and we want to encode the whole novel or a very big poem, it would be simply impossible to fit this very big body of text into a certain value. It would become unrecoverable, which is not the idea of such encoding algorithms. Now let's talk about the checksum in back32 addresses. So the last 6 characters of back32 address are the checksum. The checksum is based on the BCH code that guarantees the detection of any error which affects no more than 4 characters. And the chance that the checksum will converge when more than 4 errors are made is 1 in 109. So it is a pretty solid encoding algorithm which is able to detect errors. One of the advantages of using BCH codes is that they can also be used for error correction. If up to 4 errors are in an address, they will be corrected automatically. So even if we have, when we have no more than 4 errors, they will be corrected automatically, which is nice because you would never even know that this address was corrupted, either when you were writing it down or when you were passing it through the internet or so on and so on, when you were saying it to someone on the mobile phone. Even if you make a mistake, it will be corrected, but of course up to 4 errors. And if more errors are made, they will be detected with very high probability, but there would be no automatic correction. So it means you know that there is some error, but there's no, well, it will not correct this error automatically. You will need to request another, you will need to request the same address one more time to hope that this time you will get either an address which has not more than 4 errors, or ideally no errors at all. Now let's also have a brief reminder of digital signature and kind of tie everything together to understand what role does it play in Bitcoin, and in what are we talking today in this lecture. So the signature process is pretty simple. We have a message, we have a private key. They act as the input of a signature function, and this function outputs a signature value. In order to verify the signature, we first need to obtain the signature itself. Digital signature is included either in the transaction itself, or if the transaction was created with a segregated witness update, the digital signature that proves this very digital signature that proves the ownership of the coins is transferred together with the transaction, but is included in a separate structure. So it is not included directly into the transaction. And in order to prove that someone is spending bitcoins from their address, so they have the right to spend these bitcoins, they need to publish the public key. This public key will be hashed according to the algorithm and compared to the address. So in other words, the hash value of the key needs to match the address, and in addition to that, the digital signature of course needs to be valid. So we get the original message, what was signed, digital signature value, which can be together with the transaction or not, and the public key, and verify the signature. But of course in Bitcoin we have to hash the public key to obtain the address as well. As for cryptography in Bitcoin, let's also have a brief detour and look more specifically at the algorithms that are used. So basically, Bitcoin stands on these 3 whales of cryptography that are SHA-2 hashing algorithm, which produces hash values with the size 256 bits, RIPE-MD hashing algorithm, which produces hash values with the size 160 bit, and EC-DSA digital signature algorithm based on elliptic curves. And these three algorithms are enough for Bitcoin to exist. Basically, it needs nothing more, and it can work just fine only with them three. Of course, Bitcoin script, for example, uses additional hashing algorithms such as SHA-1 and SHA-3, but they act as the addition to the main protocol. They are not vital, and protocol will not stop working without them. It's just additional functions that allow you to create certain conditions when making your Bitcoin script. And of course, recently, Bitcoin has received Schnorr signatures. They have been added to the protocol. Now, since we are talking about transactions, not only addresses, but transactions as well, let's talk about the concept which is called triple entry accounting. But wait, triple entry, if we have triple entry, there should be double entry and single entry, right? And this is absolutely correct. Let's walk through each of them. So, when accounting systems were only in their inception and financial operations in the society were not as complex as they are today, there usually was a certain person or an entity, maybe an organization, which took care of the accounting. And this organization or person used digital ledger, maybe even, well, if we go way back into the history, they were using some stone tablets or something else, and they were writing all of the transactions into this ledger by hand, with a rock, with a pen, whatever, it doesn't matter. And this is called single entry accounting, because there's only one ledger, and this one ledger is maintained by one entity and has all of the transactions. So as you can see, it may work for, I don't know, for some tribe of primitive people, but as the trade and financial relationships have been becoming more complex, there became more entities, and the nature of the relationship also became more complex. So the parties who were transacting among each other realized that each of them can keep a copy of the ledger and check it with the other party. So and they don't need to keep the complete ledger, because what is debit for one side acts as credit for another side. So they only need to reconcile these changes, and they can compare their books from time to time and see that everything is reconciled. So debit and credit matches. There are no money does not appear from the thin air. And actually, most banks today work according to this approach. They use double entry accounting. So as you see, we have Alice's company and Bob's company. What is debit for Alice acts as credit for Bob. So when they put these ledgers one next to each other, they see that for Alice's account was debited by 11 units of money, and Bob's account was credited 11 units of money. And the same goes here, but vice versa, and the same goes for the rest of the entries as well. When Bitcoin appeared, it led to the situation when both transacting parties keep a complete history of transaction or history of transactions, while everyone else in the transacting in the accounting system act as the third party, as a kind of an auditor, guaranteeing that the chronological history of transactions and transactions themselves are in place. If they fall out of sync or need to catch up, they can do that based on other participants of the system, while at the same time verifying that transactions are valid and the distribution of coins indeed happened. And this is triple entry accounting. So they both keep complete history, and this is what is stored in the, it's important, distributed and shared ledger. This is what everyone keeps. And if I fall out of the loop, I can hop on, I can look at the distributed shared ledger and see, okay, debit minus 11 for Alice, credit plus 11 for Bob, and so on and so on. And I can check, as we have I discussed before, I can recreate this state of the system for myself and see that everything works. Of course, as long as I have at least one adequate friend, player, or system participant who can give me the correct data. But if, of course, I connect to the person who is feeding me invalid data, it will not be too good. That's why it's best to have at least several parties in your neighbors list. Okay, so here, let's have a little investigation. Let's have a little quest where in which we will be looking for well, you will see what are we looking for. I will explain everything as we go. So before, we have discussed that fee in Bitcoin is calculated as a result of subtracting inputs from overall coins spent. So the difference between the inputs and the overall coins spent is the fee. This difference is considered to be a fee. We sum up all inputs, we sum up all outputs, subtract one from another, and get the fee that a validator will receive for its work. Here, we see that the body of the transaction with its inputs, outputs, and script pub keys. The thing is that we have value in outputs, but we have no value in inputs. Then the question here is, how do we know the sum of inputs? Knowing only this data, how do we know the sum of inputs? And let me explain you how do we do that. So we look at UTXO, at unspent transaction outputs. But this begs another question: how to find the UTXO that, for example, this specific input spends? And in order to find this UTXO, we first of all look at the value in the hash field, and this points at the transaction from which coins are spent. This points at a previously unspent output, which will be spent by this input. And well, this is a pretty big transaction, right? It can have many outputs. And how do we know which output is specifically connected to this input? And that's why we have another field, which is index. And index shows precisely which output of this transaction will be spent. So first, we look at the transaction by its hash, and then we look at the output. So in order to calculate the total inputs of this transaction, we look at the hash of each transaction here and look at an index, and then we sum it up and do this calculation to get the fee. So this is what concerns transaction inputs and outputs. And now let's have some statistics to maybe have a little rest closer to the end of today's lecture from all this pretty complex and technical stuff. So let's just have some fun and relax with some statistics. Here on the graph, we have the average number of transactions per block. As you can see, for the past few years, the average number of transactions per block is roughly around 2,000. If we really approximate using our eye, it will be around 2 per block. Considering that one block appears roughly every 10 minutes, well, this is what protocol aims at, we can approximate that every 2 minutes, 2,000 new transactions are confirmed in Bitcoin. So I feel like someone had one of these questions before, either about the number or about how many transactions are confirmed. So here we are answering this question, even with a nice little pretty graphical representation. And of course, average number of transactions has grown substantially compared from 2009, when Bitcoin was in its inception, in its early years, and we have this very big growth here, then a drop, and since then it was more or less stable for Bitcoin. Now let's look at another piece of statistics, the number of unique addresses that are used. And here, first of all, let's clarify, what does this mean? Unique addresses used. Used means that this address has at least one unspent output, simply meaning that this address has some coins. New addresses can appear when a user creates a new address, new account, or new unique address, used address, can appear either when a new person creates a Bitcoin address and becomes a user of the Bitcoin system, or when an existing user creates a new address in order to receive new coins and funds this new address. Of course, the number can also fall, as you see from here especially, and the number of addresses falls when the coins on the address are spent. So when coins on the address are spent, there are no unspent outputs for this address. It is not considered here, so it becomes unused. It is not active, it is unused, and it has 0 coins associated with it. So in addition to the number of unique addresses, this can show the relative number of users and the popularity of the network at the given time period. So again, we see that here we have this crash. So people have been getting rid of their accounts. So either everyone were consolidating coins on one addresses, or most likely people were transferring coins to the addresses of exchanges in order to exchange coins and receive fiat money. and the coins were consolidated on addresses of centralized exchanges. And another graph is mempool transaction count. As you can see, it's very jagged, and here we have the one more splash in this area, and the number of transactions in the mempool, and by that we mean the number of valid unconfirmed transactions waiting to be confirmed, can vary really significantly. So from a few thousands to tens of thousands, like here. And as converting this into megabytes, we can roughly say that the mempool size can vary from few megabytes to several dozen megabytes. So here you can see this volatility range, this amplitude of mempool transaction count. And here we have a similar situation, but it shows the mempool bytes per fee level. So the colored layers represent the price of Satoshi per byte. So this is 1 Satoshi, this is like 10 Satoshi, the red one is 23 Satoshi, and so on, so on. And they are ranged from the lowest to the highest. The cheapest transactions are at the bottom, and the most expensive ones are at the top. And it's interestingly to see as the mempool size grows, so we have more and more and more transactions. This is the body of transactions. As the mempool size grows, the proportion of transactions that pay more also grows. So you see here we have very little of the reds, and here the reds have grown substantially, and the same goes for greens. They have grown even more, and yellows grew also a little bit. And this goes in cycles. So here they processed, or the workload on the network has fallen. Validators have processed transactions, average price has fallen. Then again, it grows, reaches the peak. Again, proportions are growing for these transactions, and the peak falls, and so on and so on. For example, here, interestingly, we have a very, so if here it's more or less like growing steadily, so it just grows steadily. Here we have a very quick jump, so it goes from here directly to here, so like half a megabyte in well, so sorry, not megabyte, I mean the number of transactions has grown substantially. So the proportion of the ones that paid the most also has grown immediately. So others couldn't even catch up, and all of them had to pay more for their transactions to be validated. And here is the same graph, but it is represented a bit differently, and well, of course, with different colors and with different proportions and for different time snapshot. But overall, the pattern goes the same, and you also can see that proportions here grow. And based on this, looking at the highest and the lowest price, you can approximate the fee that you want to pay in order for your transaction to be validated in an adequate amount of time. But well, do not overpay. Do not overpay without really needing to do so. So this is it for today. I don't see any questions in the chat, but maybe you were waiting to ask something right now. So if you do have something, then let's have a chat. Let's discuss your questions.
Hi, Alexei. Thanks for such interesting lecture. I've got a question about checksum in back32 addresses. You said that that address can be corrected automatically if there are less than 4 errors. And the question is, like, why such error can appear and at which stage, and like, who can make such errors?
Yeah, I see. And Igor, I also see your question. So yeah, let's go one by one. So in order to answer this question, we need to make a very brief detour to information theory. So any kind of information is transmitted in through some environment. So it can be air for radio, it can be wires for internet, it can be even if you have the USB drive and you put it into the computer, we have the transmission process. And due to the nature of the environment, due to the nature of the transmitter, and due to the nature of the recipient, this may happen in such a way that there is some corruption. For example, I don't know, if we are transmitting radio with amplitude modulation, for example, or with, let's say, with frequency modulation, because it's more popular, the radio waves are meeting obstacles on their way. And that's why the wave is not, the wave reaches the recipient already in a different form, because it has met trees, like walls, cars, people on its way. So it may become corrupted, and this is where we have these errors. When the recipient does the decoding process to obtain the initial message which was passed, he will decode something different. And here in this moment we notice that there are errors. And here's a very, very simple example with the this game, like Broken Phone. You know this game where you whisper something to the person, and then the person whispers something else, and this goes like 10 people, for example. This is a perfect example of how the original message can be corrupted due to this process of transmission, because they said it too quietly and you didn't hear it, or B, someone just has not very good hearing abilities and they heard it wrong, or so on and so on, and the original message is not well, it becomes corrupted. And the same goes for Bitcoin addresses. For example, if you are sending it, I don't know, it's hard to provide a real example, because we are using nowadays we are using HTTPS protocols, which, and all of this infrastructure of the modern internet already includes some error preventing encoding when we transmit the information, right? So it is unlikely that when I send you my Bitcoin address, it will become corrupted simply because, I don't know, my Wi-Fi is acting up or my computer is acting silly. It's not the fact in the modern environment, but if it is really happens so, then this correcting encoding codes like BCH, for example, can do that for you. And the most direct example with Bitcoin addresses is we are on a call and I am telling you the address one letter, one character at a time, but the phone connection is bad, so you cannot hear everything well, and you got a few characters wrong. So here we have the corrupted address, and the BCH codes can correct such errors. So I'm sorry if it was like too long answer for such a question, but I hope it makes sense to you why such codes exist and how do they work overall.
Yes, this is quite complete. Thanks.
Okay, great. Yep, Igor, what is your question?
Thank you. I have several questions. One of them related to previous question, and how it's possible system automatically correct address? How can it know the correct address to correct to it? I don't understand how it's possible.
Yep. Okay, I will answer this question first. And well, the thing is that the system does not know that. And this is the algorithm itself, which includes error correction methods. They are, well, it will be probably impossible to explain it right now, but this is not something which exists in Bitcoin. If you try to look it up on the internet, just search for something like error correcting codes or error correcting encoding and so on. You will find more information, but overall this is done on the encoding level. So this BCH codes, for example, they use math in order to correct the error. So the algorithm itself, the protocol, the encoding does not know what is right. It's not like it keeps it somewhere in its head and looks, oh, we have a wrong character here, so we need to delete this one and substitute it with a different. No, it is done through certain low-level operations and basically through math in order to do this correction. This is a very interesting topic, but it's too big for us to have any adequate explanation here. If you want, I can send you a few links for something of that regard. But it's
Okay.
basically not on the protocol level, it's the codes
Okay, I see.
that
Thank
do
you.
the job.
If possible, please send us several links. Maybe we will understand how it works. Okay.
Yeah, it's a very interesting topic, so I highly advise looking into it.
Okay, thank you a lot. Another question related to topic you started at the beginning. So you said that public key is generated by like a kind of summing private key several times. And for example, if private key is 2, we sum 2 plus 2, and it will be public key. Did I get you correct? Or it's have no sense for me, because we can calculate public key, or we can calculate private key knowing public key in this case, or not?
Not really so. So it is again the nature of elliptic curves, and in reality, and as I have said, your private key won't be like 1 or 2. It will be an extremely
very
large
big
number, and it will be truly random number. So by having only the public key, it's impossible to know what was my initial number, because you will need to do this addition very, very many times, and it is practically impossible to do this in any kind of meaningful time frame. And this is basically the idea of doing this operation.
So public key is always bigger than private key in this case, yeah?
It's not really bigger, because we are doing, well, it is the point on an elliptic curve, so it has coordinates on the elliptic curve, so it is not really like it's bigger or smaller, whatever. a different representation of, and we are adding the point to itself. And since we are operating in the elliptic, we are doing elliptic curve mathematics, then the operation of this addition is not the same as arithmetic addition, for example. We are, well, it's a bit different from simply doing the arithmetic addition. And
could you send some maybe also articles, maybe, or
I
I can
think
Google, maybe if you know some good.
I would say that if you haven't requested our books yet, I highly advise to do so, because we have a significant body of text on cryptography, and specifically on cryptography, which is used in Bitcoins and other decentralized systems. And there you will find all of the answers for the questions you have regarding the elliptic cryptography.
Okay. Another question. It's theoretically possible that me and you generate the same private key, regardless it's a very random and big number, but theoretically it's possible. Is it problem?
Well,
Or
it's, I mean, in pure theory, it can be possible, but how, well, it's the same as how possible is that you and I, when we are throwing the, we are rolling the dice, right? And the dice has numbers from 1 to 6. How big is the chance that we roll the same dice? So we both rolled the dice, and what are the chances that we roll the same dice? Well, they are pretty fair chances, right? Or if we flip a coin, for example, again, chances are even higher that we flip the same coin sooner or later. But when we are operating in on the elliptic curve, and we are generating a random number as big as a private key for the elliptic curve digital signature or whatever, then the chances are very small, and especially if we are using proper algorithms with proper randomness that provide the level of randomness which is very close to the true real randomness, then it's even less likely. Because why am I saying true randomness is that basically any random number that you're generating on the computer is pseudo-random number. It's not truly random. It only acts as the random number, but it is generated according to some deterministic algorithm. And there are many algorithms that can generate seemingly random numbers. But if the algorithm is not proper, it will become predictable. And in that case, of course, we can start observing certain patterns and even try to guess what will be the next random number. And this is a big problem for such algorithms. So that's why when generating something, we need to be sure that the algorithm is truly random.
But anyway, it's not even a big problem, yeah, if you and I have the same private key, because we don't know about it. Yeah, there is no there is no reference for me to understand that you and I have the same private key.
Well, I mean, even if it so happens, then it means then that you basically have guessed my private key. So you will own the same coins that I do. And this is basically a brute force operation, right? You are flipping this coin until you get a value which corresponds to someone's address with coins on it. So I can generate these private keys again and again and again and for each private key I generate, I also check whether I can associate some address with it, and if I can associate some address with it, and if this address has coins on it, then jackpot, I have got myself some free coins.
Yeah, it's only like I mean straightforward. Okay, thank you a lot. And last question, please, if possible. And I think it's maybe it's under NDA, but just if it's under under NDA, okay. Just understand, in your daily work, you use some hashing algorithms. I don't know, some other cryptographic algorithms. And do you write it by your own on C++, or you also use some libraries? Because I'm like as iOS developer, I use already like out of the box provided algorithms and implementations.
Yeah, this actually is a very good question, and I think it's important to know this in advance, and it's important to not be ashamed to use libraries, modules, frameworks in your daily work, and especially in commercial work. And the reason for that is one of the main rules of programming is to not reinvent the wheel, right? Unless you really have an overaching reason to, I don't know, re-implement SHA-256 algorithm, for example, from scratch. And we are not talking about educational purposes. For educational purposes, you need to implement everything you see, like 2FA algorithms, hashing, encryption, elliptical curves. The more you implement, the better, because you will learn it from inside out. But in commercial practice, and any commercial company which appreciates its time and wants to sleep good at night are using public open source implementations of especially of standards, right? Because, for example, there's a very good library called Bouncy Castle, and this Bouncy Castle library has a lot of cryptographic primitives, operations, standards, and so on. It has been maintained by a group of people for years, and they have been monitoring, updating, and improving, fixing bugs, and so on for years. And it's simply impossible to do something better than them if you are doing it from scratch, because these people have been doing it for practically all of their life, right? And that's why you feel confident when you are using these open source libraries, and because they are supported by a team of people and they are audited by the community. So if someone comes and sees an error, they will find it, they will open pull request and say, hey guys, this is not good, you need to fix this. And that's why it is, well, no shame in that, and actually it's even a better idea to use open source libraries.
And at our homework, we have a task to generate key pair and digital signature algorithm. And I don't understand, should we use something already out of the box, or should we try to create some simple own implementation, or just use some protocols and just any implementation you want, either yours or something out of the box provided?
For the purpose of this course, it's well, of course, it will be more useful for you to do it yourself. And we are not asking you to come up with a new encryption or hashing algorithm, which would, well, completely from scratch, but take some existing algorithm, understand it, and simply code it yourself. Even looking at the pseudocode, for example, it would be very useful for you.
I see. Thank you a lot. Sorry that I took so much time. Thank you.
No, it's
had a lot of
okay, and
questions.
thank you for the great questions. And one final note, as I was talking about the brute force and all of this thing, and it reminded me of one little tool that I have played with, although I must admit I wasn't really successful, but maybe you have some time or you have a good computer and you can play around with it. The tool is called Plutus. I sent the link in the chat, and this is it's called an automated Bitcoin wallet collider that brute forces random wallet addresses. And I think that personally for you, Igor, it will be really interesting and even useful, I might say, to play around with this program and see for yourself what are the odds of well, generating around the same private key as someone else. But it's an interesting experiment. I played around it with it myself, and well, haven't got much, only empty addresses mostly, but still it's pretty interesting.
Thank you.
Okay, so if we have no more questions, then we can close today's session.
Okay, thank you for a lot, Alexei. Thank you for a lot for all our students. And please waiting for our task and our materials. See you soon. Goodbye.
Yep, thank you. Bye-bye. See you.
Bye-bye.
Thank you.